All right, so here we go with the molar volume of hydrogen lab, okay? And the chemical reaction we're dealing with is magnesium plus hydrochloric acid is going to produce hydrogen gas and the magnesium chloride aqueous solution. This is a redox reaction, and we're using the action of the acid, in this case, the proton released from the strong acid, to oxidize the magnesium or be an oxidizing agent to produce the hydrogen gas. So, the system is important to understand is that what we're doing is we're collecting a gas by water displacement. That's my wavy water, okay, if I guess it was dark like that. And what we have is a eudiometer, hope you guys get it, which is our tube that's calibrated backwards fashion. I'm not loving this marker, but maybe it darkens over time. And of course it starts with 0 up here because it's an emptying device. You're measuring the volume. Now, what we did is we had some magnesium, okay, and I'll just use, we had magnesium being suspended by a copper wire, okay, and now my copper wire be red, okay, we wrapped it around it and round it to the outside, and we measured that magnesium to a certain mass, okay. I filled that eudiometer tube with some amount of acid. It was upside down before we capped it and inverted it, and essentially, so again, just to make sure you understand, we had a tube, a eudiometer tube. We filled it about a third of a dilute acid. We took a known mass of copper ribbon. We took copper wire. We wrapped around it, okay? We inserted it into the tube. And then we wrapped the wire on the outside to hold it to it. We then filled it with water, okay? So the acid was still on the bottom to the top. We put our thumb on it, inverted it, okay? And we have this completely filled. Now, the acid dropped through the tube, and you know the reaction was occurring because bubbling occurred. Hey, we're producing a gas, okay? And we were collecting the hydrogen by water displacement. So when the acid dropped and was in contact with the oxidizing agent of the H plus that was produced, okay, or released by the strong acid, it produced hydrogen gas, okay? Now, we're collecting over water. So anytime you collect over water, you should recognize the fact that we're not only collecting this gas, but what else are we collecting? Water vapor. And that's why you took the temperature of your system. I'm going to say the temperature of my system was 22.0 degrees Celsius. I should have a tenth in there because our thermometer is measured to the individual integer. You should have a guess there to the tenth place. Okay, so this bubbled all the way down and it stopped. It stopped because the magnesium was the limiting reagent. It ran out, and therefore the reaction stopped. The hydrochloric acid, however dilute, was in excess. Okay, so I've got a couple of things I need here. Okay, first and foremost, I need a volume of the gas collected. And I say gas, but it's gases because we know every time we collect over water, we're getting water vapor. So I need that volume, okay? And that should be to, I think, the hundredths place. I think the individual tenths are calibrated on that eudiometer tube, if I'm not mistaken, okay? Any case, that's going to give me something to the milliliters. Also I need, okay, because guess what? We have a height of column of water, okay? We have to measure this distance, this height of water. And of course, we need to have what? The outside atmospheric pressure. Okay, so I'm going to pull up now your lab, okay, so we can see what we're doing. So I'm going to view this. All right, boom, lab 20. Make this up close and personal as we can. Okay, and let's go see what we have here. So you guys should have a mass of a metal. We're going to need that at the end, but I'm going to make mine, I'm making some numbers up. So I don't know what my data is going to look like, but I'm going to make mine to be 0.07. So the mass of my magnesium for me is going to be 0.074, and that's of course grams. All right, you should have that mass. Volume of the two gases, you should have that down. Okay, well that volume for me of the gases, I'm going to make that a nice 70.10 milliliters. Okay, I got my temperature of my water. Okay, that's the temperature of my system. The barometric pressure is 30.3 inches. Okay, I can put that in there as well. You can see that I'm gonna need some units here. Okay, moles of magnesium used, I'm gonna need that later. We can convert grams to moles later. Okay, height of column of water. Okay, I measured this, maybe. And so maybe I get 30.1 centimeters. Okay, that's what I'm gonna put down. All right, height of column of mercury. Okay, now, why do I care? Because the first thing I need to do to solve for the molar volume is I need to know what the total pressure is in here. Okay, this is a manometer problem. Atmospheric pressure is pushing on the liquid that's supporting this. Not only is atmospheric pressure supporting the column, it's pushing back against the pressure here. That means the total pressure in the udiometer is less than the atmospheric pressure by that amount of supported mercury. We have water. Well, I know that mercury is 13.6 more dense, so I'm going to take this height and divide. Okay, so I'm going to take the height of column, I divide by 13.6, and I'm going to make sure this height is in what? Is in millimeters, because millimeters of mercury, of course, is a torr, is a unit of pressure I can work with. Millimeters of water is not one that we have an equivalence for, although we could find one if you wanted to do that on your own time. Okay, so I'm going to take 30.10 centimeters, and I know that simply because of the video, I know that 1 centimeter is 10 millimeters. I know it's silly. You get 301 millimeters, and that's for me water that's being supported. That's H2O. Okay, so I'm going to divide by 13.6. And again, for those that don't know I'm doing that, mercury, supporting of mercury liquid, obviously is a pressure unit. So this is going to take the support of water, it's going to make it shorter. Mercury is heavier. So the height that mercury would be there would be 13.6 times as high. I mean, as divide by 13. 13 times smaller than 301. So if I could just clear my calculator, okay, and now that I have my glasses, that would help. Okay, I'm going to take my 301, divide by 13.6, and what I get is I got 22.1 millimeters of mercury being supported. So for me, this is an important number. 22.1 millimeters of mercury is really what the equivalence of what this water is. Yes?
What was the 30.1 from? Is that your measured value?
Yeah, that's mine.
Okay.
Okay, I measured 30 centimeters, okay, of water being supported. Okay, whatever you measure. But I times it by 10 to make it into millimeters of water, divided by 13.6 to now give me what the height of that would be if it was mercury. Why do I do that? It's a pressure unit. Millimeters of mercury is a torr, okay? Same thing as 21.1 torr. Okay, and I can relate that to atmospheres. Okay, which I'll probably do later. Okay, partial pressure of H2 in the udiometer. I need to know the individual partial pressure of the H2. That's important. Okay, so I need a total pressure. Okay, so I'm after the total pressure. Why am I after? Because I know the pressure total is equal to the partial pressure of the water. Remember, anytime we collect over water, we're going to get water vapor, plus the partial pressure of the hydrogen. Okay, I need the total pressure. That's what I'm after first. Okay, well, this is a manometer problem. I have 30.3 inches of mercury pushing down, and it's supporting this amount of mercury as an equivalent to water, plus it's pushing back this pressure. So I know that this pressure inside is less by that height of column of water. Okay, I'm in inches of mercury, we're in millimeters of mercury. So let's convert to millimeters of mercury. So I'm going to take my 30.30 inches, okay, of mercury, and I know that there's 2.54 centimeters in 1 inch but I can do this in one step. If it's 2.54 centimeters in 1 inch, isn't it 25.4 millimeters per inch? So I'm just going to make this one step, 25.4. And if you didn't know that conversion, I would give that to you. And so what that gives me is that's going to give me in torr or millimeters of mercury what the atmospheric pressure is, not in inches of mercury, which I can't really use in any of my equations, 30.3. And of course, I'm going to times that by 25.4. Okay, and this gives me 769.6 for me. 769.6. I'm going to call that torr, which is the same thing as millimeters of mercury, because Torricelli was the guy who first used that to solve that problem we talked about. All right, so that's the atmospheric pressure. So I know the pressure pushing down. Remember, I can relate this to a manometer. How can I do that? Okay, well, here's my gas. My gas is it winning or losing? It's losing, right? So we're going to have what? It's losing by how much? Assuming this is mercury, it's losing by what? This would be what? 21.1 millimeters of mercury, correct? Good. We know pushing down is what? 769.6. So to get the total pressure, I'm going to subtract the 22.1 from 769.1. That's what I'm doing here. So 769 point, what do I have? 6, I think. Yep. And I'm going to subtract that by 22.1. And I get 747.5. So my total pressure here is from this math using a manometer, okay, is 757.5. Don't forget we're in torrs now. Okay, so what's my partial pressure of my water? Well, that would be the vapor pressure of water. Okay, so we need to go find our vapor pressure of water. So party people, let's go back. I think, oh, there's a table. So I'm going to view that table.
I'm pretty sure it's 747.
Okay. I don't think it's 747. That's be a lot. But I have 22.0. So based on my table, we know that the vapor pressure, the force of gases becoming a liquid, is a function of temperature only. So I have 22.0. So the vapor pressure is 19.835. 19.835. That, of course, is torr. And, of course, based on what? This, my friends, is Dalton's law. This, my friends, was the what? Manometer problem. Manometer problem to read the total pressure. Yes?
Can you scroll down just a little bit on there?
Or scroll up. Is this up or down? I don't know. Oh, my mouse. Is that good? No. Other way?
That's good, thank you.
Okay.
Wow. No, it was right.
So to solve for my missing, remember, I collected some water vapor, and the rest of that pressure is due to the hydrogen. So all I'm doing is subtracting the water vapor from the total. So 747.5 minus 19.835, and I get 727. So my partial pressure due to the H2, which is an important one here, is 727 point, and I'll do it to the 10th place, I think 4 significant figures, 0.6, I'll just put 0.69. And that's torr, don't forget, everything was in torr, or millimeters of mercury. All right, so that now, let's go back to the lab, labo fun, okay? And nope, I don't want to go smaller. Let's get bigger. And I think I'm here somewhere, with my thousands of tabs open. Ah, here we go. So there we go. Hey, what's the partial pressure of the H2? There it is, for me. Partial pressure is based on the water. Okay, now we're going to get somewhere. What am I after? I'm after the molar volume. What's the molar volume? Molar volume is the liter per mole. That's a molar volume. What should we get, you think, per mole of H2? What should we get? Did we decide a mole is some amount at STP?
Oh, yeah.
22.4. We're going to see how close we get. Okay? So I need to know, okay, a pressure fraction. We say, why do I want a pressure fraction? Well, the fraction of the pressure is a fraction of the volume. Gases that are in a mixture are behaving the same because they're in the same conditions of what? Temperature and pressure. Avogadro's hypothesis is what we're really talking about. It's another application of Dalton's law. I want to know, of the volume that I measured, what is the real volume of just the what? Hydrogen. Isn't this the volume of both gases? How can I get the molar volume if I've got two gases in here? Now that I know the fraction of what the pressure is, shouldn't that be a fraction of the volume? More molecules, more space. Same molecules, same space. Remember Avogadro's hypothesis? That N is what? N is proportional to volume. So what I'm going to do is find a pressure fraction. It'd be the same as a what? Mole fraction, volume fraction. They're all proportionate. So I take my 727.69, which is the part over the total, 757.5 torr, and I'm going to come up with a decimal. Of course, less than 1, but it'll be pretty high. So 727.69er divide by 757.5. Okay, what do I get? I get 0.961. It's got no unit. This is torr over torr. Mole fractions have no unit. So this is my volume fraction. What does this mean? 96.1% of the total volume is due to hydrogen. Why? Because 96.1% of the total pressure is due to 96.1% of the total molecules. Okay? Don't lose sight that this is something you need to understand for your test as well. Okay, that's why I'm doing it. Okay, I got a pressure fraction. Cool. Okay?
So is that 0.961 the fraction?
Yes! Yes! It's the same pressure fraction. What if I ask for a mole fraction? Would that be the same? Yes! So now I have a what? It's the same. So that is my pressure fraction. That is my now volume fraction. Okay. What's the volume due to the hydrogen? Well, what's my total volume? What was your total volume you measured? In my case, it was 7.10. I'm going to find 96% or 0.1% of that. So I take this volume fraction, and I'm going to times it by 70.10 milliliters. Don't forget what this is. This is the total volume of your gases. I want to find what the volume is due to the hydrogen. So I'm going to take my 0.961, times it by 70.10. Party people, that is now going to be 67.34. For me, it's 67.34, and that's milliliters because there's no unit there. And that equals the volume of dry hydrogen. Okay? And this is corrected for H2O vapor. Okay? Now, number 10. What are we after? I want the volume of 1 mole of it at STP. Why? Because I know it's supposed to be 22.4 liters, correct? So here's what I'm going to do. I'm going to get rid of this because we don't need this anymore. Okay? So here's what I'm going to do here. I want to correct for this volume for STP conditions. Currently, what do I have? Okay? I have a volume. And I have a pressure. What's the pressure? Okay? I have a volume that is, remember, PV over T equals PV over T. Moles are staying constant. I'm going to correct for STP conditions. My new condition will be, what's the volume when the pressure is 760 torr? Isn't 760 torr 1 atmosphere of pressure? Yeah. Okay, cool. Temperature at STP is 273 Kelvin. Okay, what's my current volume? 67.34. That's just for the what? Hydrogen. What's the temperature of my system? Well, 22 plus 273. Remember, you have to be in that. So for me, it's 295. I'm just going to change my volume, what it would be if it was STP conditions. Now, I can't use the partial pressure. This gas is flying in with this pressure. That's important. I can't use its partial pressure. What is the pressure it's under? It's under that pressure. That's the trick there. 757.5. Now just stay with me for a second. I'm running out of time, but I'm going to solve for that volume. It's going to give me what the volume would be if we were perfectly at STP conditions, correct? Good. Next step. Convert this to what? Liters. You with me? Hold on. Once I have liters, last part, I'm going to divide by the moles of what? H2 that I should have. When you balance this equation, 2 chlorines, put a 2 here, 2 chlorines, okay? That gives you 2 H's. 2 H's are here, it's balanced. So when you balance this, there's a 2 here only. The same number of moles of magnesium should give you what? The same moles of hydrogen. Take your moles, take your grams of magnesium, do what? Convert to moles. That's stoichiometry. That's the moles of hydrogen. So divide this by the moles of what? Moles of magnesium, which is really the moles of what? Hydrogen. And you'll get that because of using the grams that you collected. And now you're going to get liter per mole at STP, and that'll be your molar volume. Okay? That's how you do these calculations. All right? See you tomorrow.
Mr. Brock, do you have